f of a is sine of a over x minus a. And very similar to the cosine proof, I'm sort of stuck here. I can't factor. Identities are going to come to our rescue. And the identity is 2 times cosine of x plus a over 2 times sine of x minus a over 2. Okay, that's the identity that comes. So sine of x minus sine of a, this expression is equivalent to that expression. I could again do my little calculator test, and you could plug in sine of 13 minus sine of 2, and then I could plug 2 times cosine of 13 plus 2 divided by 2 times sine of 13 minus 2 divided by 2, and I get that same, funky decimal, all right? Okay, so same little trick, we'll break it here, and so the limit of a product is the same as the product of the limits. So the limit of that front factor times the limit of the second factor is equal to what I started with. And I strategically put the x minus a with the second factor. Like it was in the last problem, that's equal to a half. So we got rid of the 0 over 0 by realizing that it was in a special form that we know gives us the coefficient in the sign, and that coefficient is 1/2, and so it turns into 1/2. How you actually prove that, you need to cover stuff in Calc 2, so that's why I'm not, aside from just showing you the pattern that we got exposed to in some of our other examples. In Calc 2, you'll go over methods on how to figure out why we get that coefficient. Okay, so this turns into a half. I'm then left with 2 times cosine of x plus a over 2 times the half. The half cancels the 2, and I notice that I'm no longer getting that indeterminate form. There's no divided by 0 anymore, so I can just go ahead and plug in my value, so I get cosine of a plus a over 2, but just like before, a plus a is 2a, and the 2's cancel, and I get cosine. So the rule for sine is the derivative of sine is cosine. No negative in front of it. If you had written it out with the x plus h version, you would have done that same substitution. That you'd use this same identity. It would look a little different because you're using x plus h and x, but you basically use that same identity and it works out the same way. If we graphically look at this, I'm going to erase minus sign. Okay, if we graphically look at this, the graph of sine starts at 0, and then at pi over 2 is where it hits its maximum, and then at pi at 0 again, and at 3 pi over 2 it hits its minimum, and at 2 pi at 0 again. And so if we go through the slope of that, initially my slope is positive, and it actually it is positive 1, and it's still positive, but it's getting more and more flat. At pi over 2, the slope is 0, and then the slope is negative, and it's most negative here, so the slope would be negative 1 there, and then it becomes less negative, and here it's 0 again, and then it becomes positive. And so if I connect those dots, you can see I'm tracing right back over the graph of cosine, which is what we just proved. If you notice these rules, I mean, they're similar. The derivative of one gives you the other, but cosine has the negative coefficient. We saw algebraically why it occurs, but thinking about the graphs is actually, when I was first having to get all this straight, that was how I kept it straight, which one had the negative. Cosine's slope starts off at 0, and then immediately after that becomes negative. So that's how I remembered that cosine's derivative has the negative in it. So you may want to use that same little trick to kind of keep the two straight.